streaming thing. So last week there was a physical science and physics seminar. These are actually prospective professors in the future that we're trying to invite here to interview, and we're having them, give a teaching talk and a seminar on their research. And I just want to encourage, everyone who is able to come on Friday. I think usually it's Friday 2 p.m. or sometimes Monday 2 p.m. And then I'll work it out with your instructor in case that's the case, that you have to miss maybe the first 50 minutes of the lab. And that way you guys can come to these research talks on mostly physics. There's one on atmospheric science, which has a lot of physics in it, but it also has chemistry, geography, biology in it. It has all kinds of stuff in it. So it's so I think it is a good experience for you guys to see like these type of research talk. That way after I graduate, what can I do, right? And no matter which degree you have. Yeah, Isaac?
20 points
each, yeah.
You get up to 80 points?
Yeah, so there's going to be 4 more of these. So that's basically like almost a full homework assignment, extra credit, right? And because you are spending time, an hour of your time out of your day, right? So I want to make sure that you are compensated for, spending extra time outside class by coming to these talks. But you do have to write a 1-paragraph summary, so you can't just show up and then eat the pizza and then fall asleep in the back or something like that. You do have to write a 1-paragraph summary. I think the first one is posted on Canvas already, so you can take a look at what's required. And then if you have any questions on the seminar, you can post that on the discussion board. Of course, you're free to ask these questions in the room, which is mostly going to be in here, so you'll be familiar with the layout. But if you ask those questions about the seminar on the discussion board, I will try to answer it myself first. But if I can't, I will ask the speaker to contact you directly. So hopefully that'll be kind of neat also. Okay. So ask questions that I cannot answer, and then you guys can actually have contact with the speaker. So this Friday at 2 p.m. in this room, it's going to be this guy, Jason Vetch. I'm not really sure how to say his name. He's from CSU East Bay, but he works at the Center of European Nuclear Research, which is in Switzerland. I also worked there for 3 years. It's a great place if you like, Swiss food, and you get to cross the border into France whenever you want. And he works on this detector called Atlas, which is on part of the Large Hadron Collider. It's the biggest science experiment ever built. It's actually a ring, and the diameter is 27 kilometers. I should have gave you guys a picture of it. And if you actually go there, one part of it is in Switzerland, and one part of it is in France. So it's too big to even fit in one country. So it's and it costs the European Union maybe like $20 billion to do this type of stuff. But they're cool with that, as opposed to shooting down balloons with these expensive missiles that we do. Let's just say that. Okay, so everyone's welcome, and I think usually they have the SPS Club sponsor these things, so they have sodas and pizza usually at these events. So but don't expect it to be like a full lunch. It'll be like a slice of pizza, right? So it's not like don't be starving. It's like, oh, I'm starving, and then you go to this to get food. Okay. Okay, so before we get started on chapter 29, other thing, right? Reminder, right? Midterm number 2, right, is next Monday, right, on the 27th, in class, in here, right, covering chapter 20. Remind me what the chapters are? 5? I'm sorry? Yeah, 5 to 28. Okay, the last 4 chapter we covered. And we'll have a review session on that on Thursday, right? Where I think on Canvas there's already a discussion board that says, okay, these are the problems I want to go over, and then I'll just pick one from each chapter, right? You guys pick one from each chapter, and I'll collate that information and try to make sure everyone has the input and get their answers, get their questions answered But if you are, that happens not to be the case in lecture, right? There's always office hours. Tuesdays, I have office hours from 3 to 4. And then Thursdays, right after that review, 3:30 to 5. So I'm available to help you guys with the homework and stuff like that. It's just a lot easier. I know some of you guys have been emailing me questions, right? But like, I have to like go to Mastering Physics, look it up. It's just much easier for you to just bring it and then help you guys with these homework. It's just a lot faster on the whiteboard versus me typing out the equation on email, right? Okay. Any questions or concern about the midterm before I start talking about Amelie Noether's theorem? Sorry. Okay. No question. Feel free to interrupt. It's not even interrupting. Contribute. Right. So before we get started, so this week, our scientist of this week, who's born this week, March 23rd, which is Thursday, right? It's Amelie Noether. She's a German mathematician slash physicist who works on these two things that at least I know her about these two things. So when I was in school, um, her mathematics. So she was actually, working on these stuff, in the early part of the 1900s. So it's the same time as like Albert Einstein, which was, who was born last week. But her work is actually, much more fundamental to what we know about physics today. So for example, relativity, which, deals with things that are moving close to the speed of light. Her work actually, allowed Albert Einstein to actually write the equations in order to, describe the mathematics. So she's making the physical and the mathematical connection between the two sides. So part of is her Noether's first law, first theorem, actually, since she's a mathematician, she does theorems. Um, it's about symmetries and conservation law. So all this stuff about conservation of energy, momentum, all that stuff that we talk about, conservation of charge, all of that mathematics, she worked out herself, right? And this is why we can actually use it. Her second theorem is actually the principle of least action, and this actually is what allowed the creation of this entire field of physics called quantum mechanics. And quantum mechanics actually allows us to have transistors, and transistors is what allows us to have computers and cell phones. So all of the technologies that we see today is based on her work in the late 1800s and early 1900s on making these mathematical connection between the physical realm and the mathematical realm, just so that we can actually write the equation to describe what's actually happening, right? This is often a lot of times what we have trouble with, right? Remember last week we did these circuits, right? You have to transcribe that into mathematics. That way we can work out the equations, right? So she did all that work in order for, people like Albert Einstein and Schrodinger, so that they have the mathematical background to actually do all that physics work with proven mathematics, as opposed to just, guessing what the equation will be and then try to plug into Mastering Physics what the answer might be, right? No one does that, right? Okay. Anyway, so let's start chapter 29. Chapter 29 is a long chapter. It has 10 sections. So on Canvas, we're going to skip 29.5, which is on magnetic dipole. By skipping, I just mean I don't have any homework on it. I'm just going to go over what those. I'm still going to talk a little bit about it, just so you can see what the result is. I'm not going to ask you questions on homework or midterm about it, so you can ignore that if you want. But it is magnetic dipole is more important than, well, actually dipoles are important no matter what. But just due to the lack of time, we kind of have to skip around. Okay. And then we're also going to skip the last section, 29.10, which is on magnetic material, right? Why are things magnetic? Why are some things magnetic? Why are some things not magnetic? That dives into the microscopic atomic structures of matter, and typically it is interesting, but it's very conceptual. So once again, since it's a conceptual thing, there isn't going to be a circuit I can ask you about it, right? So therefore, I'm not assigning any homework, and you don't have to expect any midterm problems on it. Okay. So magnetic field is very pretty to begin with. So who knows what this looks like? Anyone recognize these pictures? Right? What do they call? Aurora Borealis. Yeah, that's kind of cool. I actually got to see it twice. Once in the airplane, once in Iceland. Definitely worth a trip because a, a picture of it is actually not the right. The It's like seeing a picture of Yosemite, but actually being there. Like you just see this whole green streak, moving around up there, and and it's a very different experience. Sorry,
So we got competitors.
you get them. Okay. Well, I guess there are probably like 3D images of it already, but it's a little bit different because what you're actually experiencing, right, are charged particles that are mostly coming from the sun, right? So let's say we have the sun over here, oh, bright blue sun. Let's do a yellow sun. Have to, right? And the sun is bright, right? But a lot of the stuff that's actually coming out of the sun are not light. It's actually charged particles. Okay, so for example, a lot of them are going to be protons, which has a +1 electric charge, right? And we know that E, right, is 1.6 times 10 to the negative 19 coulomb from this class, right? When the sun exudes these protons, which doesn't even look like proton, so OT, right, right, and we're near the sun, so what happens is that as it approaches the Earth's magnetic field, and this is why this is important, right? The Earth has its own magnetic field due to the internal structure of it. What's going to happen is that these protons, which has a charge and moving, will get diverted by the magnetic field, right? What's going to happen is that let's say a proton comes in this way, instead of hitting wherever this is, what country is that? That's like Spain or something like that, right? Instead of hitting Spain, what's going to happen is that it gets bent by the magnetic field because there's going to be something called a magnetic force, called a Lorentz force, that's going to curl it, and it's kind of basically kind of pull all of this, all these cosmic rays, protons from the sun towards the poles, as opposed to the middle of it where most of the people live. Okay, and this is actually the reason why there's life on Earth, because without the magnetic field, all these cosmic rays is actually going to, these are damaging cosmic rays, so that we're going to get ionized all the time. And so without the Earth's magnetic field, what's going to happen is that all of these damaging protons is going to hit us and basically give everyone cancer, right? And then we'll all probably have to live underground, like hobbits or something. No, hobbits don't live underground, like dwarfs, right? Yeah. Okay. Okay. So let's describe how this happened, right? So we're going to go back, way back, and remember in the beginning of the semester, we have these little experiments that people talked about, well, I talked about mostly, right, where you have two charges and what happens, right? So the first experiment we're going to talk about is what is a magnet, right? So if we have one of the first experience when, at least when I was a kid, of magnets is a compass, right? A compass points north and south, right? Right. So the red needle points north, the white needle points south, or I'm always confused which one is which, but sometimes you figure it out, right? So what happened is that there seems to be something there are stuff that are magnets, right? That naturally, if you remove the friction, if you put a little bar magnet, I probably should have brought one, right, on the table, right? It's not going to move, right, because the friction of the table is stopping it from moving. But if you remove that friction by putting that bar magnet on like little cork floating on water, so therefore it's very slippery, right? Then what will happen is that there'll be one end of the magnet that's going to point north, one end of the magnet that's going to point south, right? And just by nomenclature, we're going to call that the north pole of the magnet. The south pole is going to be called the south pole of the magnet, right? So physicists are very creative in naming things, right? Which actually I appreciate, right? It's supposed to call it, jumper jack direction, something like that, or some guy's name usually, right? There's a lot of times that like, the Bill Gates direction or something like that, right? We don't want that because north points north, South points north, south, okay? Right, so this is actually kind of like anything that, even back in ancient time, this was first actually discovered, at least the documentation of it was first discovered in about 400 BC. So, 2,500 years ago, right? And this actually discovered by accident somewhere, I think, in China, where people had these iron spoons. So, people want to eat soup, right? They make irons, they make spoons out of iron as opposed to wood, right? They probably last longer, right? When they left the spoon inside the soup, what happened is that people saw that, oh, the handle of the spoon always points in a particular direction, right? And they say, oh, that's interesting. And then if they rotate the soup bowl itself, the handle of the spoon still points in the same direction. It's always pointing away. Which way is north here, actually? That way, right? Right, it's always pointing. Actually, these spoons, it points south. Okay, so they were magnetized so that this is the south end. This is the tip of the scoop part of the spoon is actually the north end. Okay, so so in Chinese, actually, a compass is actually called a point south needle. Right, very creative name. Right, love it. Right, so what does it do? It points south as the needle. Okay. So, so these magnetized materials are naturally occurring, right? So somehow there's just this stuff around, okay? Okay, and people started observing it, 2,500 years ago, and they use it to guide ships and airplanes and stuff like that, without really understanding how they work first. Experiment 2, right? That's just another observation, right? Experiment 2 seems to show that if you put two magnets that are near each other, and you say the north poles are near each other, they will repel, right? Somehow you can repel, right? And then, but if you put opposite pole next to each other, they will attract, right? You guys have probably played with these guys before, right? So somehow there's some connection with electric charge, right? Because that's the same thing that electric charge do, right? Some light charges repel, opposite charge attract each other, right? So there's some sort of connection between the two, and people couldn't make that connection mathematically, right, until the 1800s. So this is similar in effect of between electric charge and some sort of magnetism somehow. Okay. The other thing that's interesting about magnets, and this is different from charges, right? If I take a charge, let's say a 1 microcoulomb charge. If I cut this in half, right, I get two semispheres. How much charge is on each half of the sphere? 0.5, right? Half a coulomb, right? That makes sense, right? You take an orange, you cut it in half, you get half an orange, right? This is different with a magnet. Okay, let's say I take some magnet that has a north pole and a south pole. I cut it in half. I don't just get the north pole and the south pole here. I get the north pole and the south pole on each piece, which is weird, right? You cut an orange in half, instead of getting two halves of an orange, you get two separate oranges. That's just two smaller oranges somehow, right? It's like a weird situation, right? So how does this happen, right? Okay. So there's something different between charges and magnetism somehow, okay? In fact, this is so confusing, it's still confusing us today, okay? And this is known as the magnetic monopole, meaning, is there a way to keep cutting this in half, until we get to the atomic level where we only have a north pole or only a south pole? Is that possible, right? And what we did, if you even study atomic physics, is that you end up with a level of the electron where we're not able to cut that in half anymore still, right? An electron still has a north pole and a south pole, right? And this is known as the magnetic moment. This is called a magnetic moment, right? This is not going to be on a test or homework or anything like that, but it's just something interesting that we keep slicing these things small and small and smaller, trying to find a north pole. And a north pole by itself and a south pole by itself, but we can never do it, right? And there's actually experiments that are, multi-million-dollar experiments to try to look for that. There's actually multiple articles that if you guys who are at home and watching this little lecture video, you can copy that down. And you can actually see what these new results on people trying to find magnetic monopoles about, okay? But we're not going to talk too much about that because we still don't understand it, okay? The other thing is that, well, magnets not only attract each other, but also attracts some metallic objects, not all of them. That's wonky. Not all magnetic objects. So if you have a bunch of paper clips, right, that are made of usually iron or nickel, right, the magnets will be attracted to it. But if you have a penny, well, at least an older penny, maybe now there's too much tin in it. Let's say a penny is made of copper, okay, somehow is not attracted to copper. That's weird. Okay. And magnets does not affect the electroscope. Just to remind you what an electroscope is, right? The idea of an electroscope, it measures how much charge is on this little bulb here, right? So if there was no charge, right, these two little hanging metal, right, will just kind of be pulled down by gravity. But if I put some positive charge on here, right, all those positive charge will try to run away from each other, right? And then what happened is that the little flags on the bottom of it will also have a positive charge. Then they will actually push each other apart, right? So they will actually be configured like this, right? So somehow, right, a magnet has no effect on an electroscope. So somehow magnets are not making, it's not making charges. It's not a positive charge thing, it's not a negative charge thing, right? So that's the difference, right? Any questions about these 6 different observations that we found so far about magnets? Everybody's happy with it? Okay, so chapter done. We know everything about magnets now, right? All right, let's do a little bit more. Okay, I'm gonna have you guys watch this little video because it's able to demonstrate it a lot better than me jabbering. If I can get the video to play. Maybe this one. Oh, it's gonna open on a separate page. Let's not restore. Hopefully the sound comes out. Come on, YouTube. You can do it. That's why it takes so long. It's loading all the ads on the side.
In 1820, Danish physicist and chemist Hans Christian Ørsted was setting up materials for a lecture. His materials included an early kind of battery called a voltaic pile, constructed of copper and zinc plates in a dilute acid solution, and a wire held in place here by a set of clamps.
So there's a battery.
Ørsted and other scientists of his day knew that when a wire was connected between the positive and negative terminals of a battery, electricity would flow through that wire. Electrons actually move from negative to positive. However, the convention is to think of electrical currents as moving from positive to negative. So that's how we'll show it here, using red particles. Back then, scientists still had much to learn about electricity. Preparing for his lecture, Ørsted made a very important discovery about the phenomenon, quite accidentally. Among Ørsted's scientific paraphernalia was a compass. Its needle, of course, pointed north in alignment with the Earth's magnetic field.
Right. So that's just a compass that we know about from we're playing around with them.
Ørsted happened to place the compass near his battery and was startled to notice that the compass needle moved. As Ørsted deduced, this happened because the wire produced a magnetic field around it when it carried a current. If there is no current in the wire, the needle reverts to the alignment with the Earth's magnetic field.
So somehow charges moving affected the compass, right?
As it turns out, an electric current, made up of moving charged particles, produces a magnetic field that circles around the moving current, as shown by these blue lines. If you reverse the direction of the current, then the magnetic field around the wire moves in the opposite direction, and the needle on the compass flips to reflect the change in field. If you move the compass to a new spot near the wire, the needle will realign with the direction of the magnetic field in that particular location. Ørsted's accidental discovery was solid evidence that electricity and magnetism were related phenomena. The announcement of his findings incited a tremendous outbreak of research in the nascent field of electromagnetics in the early 1820s.
Any more? No, I think that's it. Okay. That's the video. And that's much better than what I can explain, right? Okay, so somehow, right, having a current created magnetic field, and this is how we're going to start talking about magnetism. Okay, so before we can start talking about things, wires, have current, stuff like that, what we're going to do is we're going to define I think we probably talked about this a little bit when we talked about torque, but what we're going to define is that, well, the problem is that, right, imagine there's a wire coming straight into the board here, right, like this ruler, right? Imagine this is a wire and it's going straight into the board, right? It's hard for me to like illustrate that without 3-dimension, right? Because I'm only able to write it on the board. So what we're going to do is that if we put a circle with an X, or even without the circle with an X, right? This is the direction into the board. To the board. Okay. If I put a circle but put a dot at the end, in the middle of it, kind of like the tip of an arrow, if you see an arrow going straight at you or an airplane going straight at you, right? You have a little dot in the middle of it, or a rocket coming straight at you. This is coming out of the board. Okay. So this is just a nomenclature so that we can actually illustrate this, into the board, out of the board thing without having to draw in 3-dimension, right? So in this case, right, we have some sort of I means current from what you guys learned from last chapter, right? There's a current going into the board because this is an X shape, right? If it's coming out of the board, it'll have a little dot in the middle. Okay, does that make sense? So we have to make sure we can understand these diagrams beforehand. And what Ørsted found out is that if you have a current going into the board, right, what happened is that the north end of the compass, meaning these little orange blobs on the side here, right? North, 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 right? Seems to be aligning like a circle all around this wire, okay? So what he figured out is that, well, that means, if we define that, well, then the compass will align in the direction of the magnetic field. So there must be some sort of magnetic field, okay? And the symbol for magnetic field is not M, unfortunately. It's B, just to be different from M, because M is used as mass and all kinds of stuff, right? So we don't want to use that letter anymore. So the symbol for magnetic field is actually B, okay? So instead of drawing a bunch of compasses, right, every time you want to indicate the direction of the magnetic field, all you have to do is just draw these lines and then just have an arrow on it, because the direction of the magnetic field is actually very important, right? Just like electric field, right? It's very important if you have electric field going left or electric field going right, right? So magnetic fields are going to be what type of quantities if it has a magnitude and a direction? It has to be a vector, right? So now we're back to dealing with vector stuff again, okay? Okay. So these are known as magnetic field lines, just like electric field lines, right? They are all going to be going around these wires, and these are going to be vector quantities, okay, somehow, because we need a magnitude and a direction, okay? One of the things is that just like regular vectors, right, a shorter vectors has a smaller magnitude, right? For example, these, right, these have the same magnitude, going around this wire. It's a different direction. But if you get closer to the wire, the magnitude of the magnetic field actually gets stronger. So it's a longer arrow, right? So a longer arrow indicates a bigger magnitude, but the direction of the arrow still indicate the same direction, right? So for example, up here, these two arrows, right? They are in the same direction, but they have different magnitudes, right? So just make sure that you guys are clear how to indicate these things, because the picture is very important, because magnetic field is going to be more complicated to draw compared to electric field, okay? Because electric field, you just have to say, well, what's the plus charge? The plus charge, all the electric field goes out of it, right? Minus charge is all the electric field goes towards it. Magnetic field is a little bit wonky. You have a wire going, you have a current going in, then you have to draw a bunch of circles, okay? You have to be very good at drawing circles, okay? And this is using what's known as the right-hand curl rule. So I think, I don't think the book calls it this. I call it the right-hand curl rule, okay? Those of you remember from when we talked about torque last semester, we had the right-hand rule to figure out the direction of a cross product, but this is a different right-hand rule, but it's still using the same hand. So if we want to figure out the direction of the magnetic field, we use our thumb to point in the direction of the current. So in this case, it's into the board, right? And our fingers are curling in the direction of the magnetic field, right? So if we have a current that's coming out of the board, let's do that. So I'm going to draw a current coming out of the board, right? So I'm drawing a circle with a dot in it. To figure out which direction the magnetic field is pointing, right? I know the current's coming out, so therefore it's going to go in this direction, right? So the blue lines, so this has some current I, and then I'm going to draw my blue line going this way instead. Okay. I'm trying to draw the vector to be shorter. Okay, does that make sense? Okay, using your right hand, right, if you know the direction of the current, you know which way the magnetic field is going to point, okay? And this is exactly what is illustrated in this tactics box with a better graphics, right? So you have a current going straight up and down, right? If you have it going straight up and down, right, your finger is going to curve on this plane like this, okay? So up, down, left, right, okay? All right, so let's draw another magnetic field line. Let's say we have a current going from the top to the bottom, right? So I'm going to draw a current, right, some current I with a direction to it. Let's just leave it outside the wires even. Okay? So can you guys tell me, how should I draw the magnetic field line? Is it going to be curving to the, let's say I want to draw the magnetic field just in front of it. Is it going to go to the left or going to go to the right? Okay, so we're going down. All right, your finger's pointing down. Which way, which arrow should I use? This one, the one going to the right or going to the left? Wait, which right are we talking about? Sorry, it may be a different right. Okay, so if we have a curve going down, right, when it comes out in front of the wire, which way what does your finger turn? It's to the left, right? So we actually want this one in front, okay? The ones on the sides are easier, right? So if you draw it this way, right, by the time your finger gets to here, right, it's coming out of the board, right? So not only does the magnetic field lines, right, are indicated by this, right, you can actually have an arrow coming out, and by the time you're able to curve your finger all the way around this way, right, it's going to be going into the board, right? So you put a circle with an X behind it, so these are all magnetic field lines, okay? By the time it gets behind the right wire, right, now it's going to the right, right? So what we do, oops, and not go to different places, right? If we put kind of like a little line behind it to indicate it's actually behind the wire, okay? And typically what you will do is you just kind of draw a circle like this, right? And then put the arrows on the line itself, indicating the direction at each point, okay? Okay. This is, you know, more of a technical way to just figure out, right? Because you can technically connect all these dots together, right? and the magnetic field will go in the right direction. Okay, I think that's what I asked in there. Okay, so that's how you figure out the direction of the magnetic field. Now come the hard part, where we have to figure out the magnitude. Okay, okay. So remember a lot when we talk about with Earth's magnetic field, right? The charges has to be both charged electrically, protons, electrons, plus minus coulombs, right? And it has to be moving. Remember when we did the Oersted experiment, when he stopped the battery from the current, when the current stopped, right, the charges are no longer moving, the magnetic field disappears somehow, right? So magnetic field somehow has to do with both the charge and some sort of movement of charges, meaning maybe like the velocity of the charge, right, somehow. Okay. So we're going to adopt a convention where when we talk about current, just like we did last chapter, as opposed to thinking about it as electrons moving, right, we're just going to think about it as positive charge moving, right? That's just a convention, and you can blame Benjamin Franklin for that, right? Back in the whenever he was doing those 1700s experiment, he said, oh, silk charge, right? No, glass charge, right, is positive, right? And that's the convention that we use, we're still stuck with since then. Okay. So magnetic fields in a wire, right, at the fundamental level is actually created by, charges. So there's going to be like a lot of these charges moving around. In a wire, mostly it's going to be electrons moving, as I mentioned, but we're going to model it as just, okay, pretend it's a positive charge moving in the opposite direction, right? Because that's the same effect. Effectively, it's the same, even though physically it's the electron that's moving. So if you have a positive charge moving to the right at some velocity v, somehow we should be able to calculate the magnetic field from it, right? Don't mix those two up, okay? The magnetic field from it, right? So as Oersted's experiment showed you, right, these magnetic field will go around, right? Or your right hand can also show you. So we have a charge going this way. That's basically a current going this way, right? We have the magnetic field curving around these wires like this. When it's close to the wire, it's stronger. When it's further away from the wire, it's weaker, right? When it's further down the line, right, it's also weaker, okay? So experimentally, we can find that, well, the magnetic field, right, that is perpendicular, meaning like right on this line, right, is going to be proportional to how much charge that particle happens to have, right? If it's a proton, then it'll have 1.6 times 10 to the negative 19 coulombs of charge. If it's a big charge, right, it can be bigger, like 1 microfarad, 10 microfarad, whatever it is, times the velocity, how fast it's moving. So these are the two things that we figured out, right? That, some sort of charge, some sort of velocity, right? Modeling it after Coulomb's law, right? Since we noted that, well, the magnetic field, the further away you are from the wire, it gets weaker, right? So we're going to first guess that, well, it should be inversely proportional to the distance squared, right? Just like Coulomb's law, right? Let me just write Coulomb's law to you. The electric field, right, is 1 over 4 pi epsilon naught times the charge divided by r squared in the r hat direction, right? So this r squared, right, goes with both, right? So there's a symmetry between the two, as Amelie Noether noticed, okay? But it will have a different constant instead of epsilon naught, right? Because magnetic field strength and the electric field strength are different. We're going to have this other constant called mu naught, okay? And I'll tell you what that number is in a second, okay? But the important thing is that this magnetic field, right, is created perpendicular to the direction that the charge is moving. You notice that, right? So at any point, right, even at this point, these two vectors are perpendicular to each other. One is pointing, kind of into the page that way. The other one's pointed this way, right? It's like a three-dimensional perpendicularness to it, right? You can have perpendicular things like this, but then this vector, third coming out, is also perpendicular, right? And this one is also perpendicular to these two, right? So they're all 90 degrees from each other, right? So when things are perpendicular to each other, I'm try and hide the answer, right? What type of mathematical tools do we usually use to find things that are perpendicular to each other? Cross product, or which trig function will tell you how perpendicular things are to each other? The sine function, exactly. Great. Okay, so we're going to go down here, and this is known as the Biot-Savart's law, because both Biot and Savart, couldn't decide who should take credit for it. Okay, so if you have a charged particle moving at some velocity v, and that has some vector to it, right? It's some magnitude and direction, right? And you want to figure out what is the magnetic field at some point, and usually we denote this point as point P. Not that P is anything special, but P stands for point. All right, and from the charge to that point P, right? There's technically nothing here, right? Just as if I tell you that I have a bunch of plus charges, right? I want to figure out what is the electric field at point P. There's technically nothing there, but you can measure it, right, by putting a test charge there. Okay. Same thing with magnetic fields, right, where there's some test point P that there's nothing there, but we can measure the magnetic field there and calculate it by taking the cross product between the velocity and the r vector. Okay, we're gonna do some fancy little three-dimensional vector stuff here. Okay, so one way to calculate this, as I mentioned, is by just taking the charge times the velocity times sine of the angle between these two vectors, right? Right? That tells you how perpendicular those two vectors are to each other. Okay? Okay. So this will get you to the magnitude of the vector of the magnetic field vector, right? Okay? And typically you will kind of want to do it this way because it's simpler, especially I like simple things, right? But how do you figure out the direction of it? Okay? This is where the cross product comes in. Okay? Okay? Cross product tells you that if you have a vector, let me just draw the little hand thing. It's going to be a horrible drawing, right? Sorry, I'm giggling at my own horrible drawing. Okay, if you want to figure out a cross product, like let's say A cross producted with B, what is C, right? That means, well, if you have A in this direction, B in this direction, your middle finger basically points in the C direction. Okay. I should have copy and pasted the picture instead. Okay, so let's say we can figure this out. Okay, so the cross product is V cross R somehow, right? So V, right, is where my thumb is going to point. Okay, R, right, is going to point this way. Notice that is actually you're not able to do that without shrinking your finger, because there are actually your hands are 90 degrees from each other, right? But it's pointing in this way. Okay, right? So there's a piece of R, right? So this is R parallel, and there's a piece of R that is perpendicular, right? Right? Because if you add those two up, right, you go, oops, that's R parallel is actually too long, right? So it's R perpendicular. Sorry. So I'm decomposing this R vector into its parallel component and its perpendicular component, right? Right? So remember that the sign wants to pick out the perpendicular part, right? So therefore, your hand also just only have to deal with the perpendicular part, right? So if my V is in this direction, vector 1, the perpendicular part of R vector is pointing up. My middle finger actually tells me which direction the magnetic field is pointing, which is coming out of the board, right? Does that make sense? Right? So don't try to bend your finger like this, okay? That's going to break your hand, okay? So try to figure out, okay, so which part of the R vector is perpendicular to the V vector? I'm going to put my index finger that way, and then my middle finger basically points in the direction of the magnetic field, right? Right. Everybody happy with the? This is going to be complicated because you're going to have to do this on every problem. Yeah.
So the milk is in the z direction?
is in the z. Well, we didn't define a coordinate system there, right? But yeah, in this case, it's coming out of the board. Okay. So if I define my coordinate to be x, y like this, yeah, that will be the z direction. Exactly. Okay. Okay. But you could define your coordinate system however you want, though, right? Okay. So just talk about this mu naught number. Mu naught number, the book calls it the permeability constant. I can never remember what these mean. Because I think epsilon naught, I think that's the permissivity constant. They both sound the same to me, right? So epsilon naught, I just call that the electric constant because it has to do with electric charge. This one, mu naught, I call it the magnetic constant. Okay. In this class, you can do that, okay? So, but if you, let's say, go on to graduate school and, like, you know, doing electrical engineering, something like that, they'll probably use this term, okay? So just be aware that it does exist, okay? Okay. And the value, interestingly, right, is exactly 4 pi times 10 to the minus 7 somehow, okay? Right? And you notice there's a 4 pi down here, right? So mu naught divided by 4 pi, right, is 4 pi times 10 to the negative 7, right? And there's a 4 pi down here. And the units is going to be this crazy thing that we're going to define in a second, right? 4 pi has no units, so it's actually mu naught divided by 4 pi is exactly 10 to the minus 7. Accident? Maybe. Maybe not, right? It's actually due to the symmetry. It's actually easier for us to measure magnetic field than electric field in the beginning. And it has this weird unit called Tesla meter per amp. Tesla, right, is actually not just a car company. It's the SI units for magnetic field, how strong the magnetic field is, okay? So 1 Tesla is an okay magnetic field, 10 Tesla is a stronger magnetic field, 100 Tesla. I don't think we can actually make that. That's too much. Okay. So this mu naught is analogous to the electric constant, also known as the permittivity of free space. So to me, if you can memorize this, good for you. Permittivity versus permeability, to me, those two sound exactly the same to me. But one of them I like to call electric constant. The other one I call magnetic constant. Okay, because mu naught is associated with magnetic fields, right? Epsilon naught is associated with electric charge, right? Electric fields. Okay, right? And to figure out how to calculate these things, we use the same techniques as what we did in General Physics 1. When we did torque, remember the thing we had to do in General Physics 1 was R cross F, right? R, right, cross F tells you about the torque. Oops, it's this finger that's torque, right? R is in this direction. If the force is in this direction, the torque will pull in this direction. And the strategies that I used last semester, and those of you who transferred in, if you need extra help on it, feel free to come by my office and then we can talk about this, right? What I like to do is actually calculate the magnitude. The magnitude is just the magnitude of R, magnitude of F, times sine of the angle between the two vectors, right? That gives you the magnitude. And you use your right hand to figure out what the direction is, right? Do the magnitude first and then do the direction separately. Okay, so why don't I do the example, which I ran out of time, the beginning of next lecture, okay? And that way we can get a little review for how to calculate magnetic field when we start class tomorrow also.